time and place notice for a technical conference and the investigation into possible amendment of Utah Admin Code R746-312, electrical interconnection, Commission Docket number 23-R312-01. My name is Mike Hammer and I'm the Commission Designated Presiding Officer. My understanding is today we are planning on having presentations from two different entities, first Rocky Mountain Power and then Interstate Renewable Energy Council, correct? Let me ask before we begin how long, let's company first, how long do you think the presentation will take?
Half hour?
Okay. And who's presenting for Interstate Renewable? All of you.
You could do an hour and a half.
Okay, well, I think we're slated for 3 hours. Or
And
something.
I mean, assuming, that's probably how much we would talk, and then assuming there would be, you know, questions or conversation, it could be a little longer, but,
Okay.
yeah.
Everyone in the room know each other? Do you want to do introductions or should we just kick it off?
We're new.
Okay, well, why don't we do that then? I just introduced myself. Go ahead.
I'm Alex Ware with the OCS, Office of Consumer Services.
Jana Saba with Rocky Mountain Power.
Jake Parker, Rocky Mountain Power Engineering.
Yeah, Lee Solom, Rocky Mountain Power Engineering.
I can go next. Kate Bowman with Boat Solar.
Sarah Puzo with Utah Clean Energy.
Brian Leidick with IREC.
Dave Molbeski with IREC.
Over here.
Patrick Grieky, Assistant Attorney General representing the Division of Public Utilities.
Doug Wheelwright with the Division of Public Utilities.
Casey Coleman with the Division of Public Utilities.
And Tammy Daly with Division of Public Utilities.
Annette Orton with the Division of Public Utilities.
Yvonne Hochul, the Public Service Commission.
John Harvey, Public Service Commission.
Fred Nice, Public Service Commission.
And Logan Mitchell with Utah Clean Energy.
And we do have some people, I believe, on the phone for the company, so,
Anyone on the phone want to chime in?
Yeah, this is Jennifer Eaton of Clean Energy.
Hey, this is Robert Meredith from Rocky Mountain Power. Can you guys hear me?
yeah, we can, Robert.
This is Zach Rogala, attorney for Rocky Mountain Power as well.
All right, Ms. Saba, are you going to kick things off with the company?
Sure. Yes, thanks everybody for being here today. The company's got a slide present. Yeah. We've got a slide presentation that I did send to the commission yesterday, so that should be on the posted to the commission's website in this docket. For those in the room, there are some printed copies that I brought with me that are over on the table. But I think most of you know me, but I'm Jana Saba. I am the regulatory manager. I do everything in front of the commission. Today, I've got Jake Barker and Lee Solomon as they stated, they're with the engineering group, so they're gonna do most of the presentation today. And then I believe I have Gillian Stanley on the phone. She didn't introduce herself earlier. Gillian, are you, Gillian, are you there?
I am, yes.
Yes.
Hi, everyone.
And she runs the interconnection group that processes all the interconnection requests that we get. She just joined that group recently, so she's here to learn, and we've got possibly the person that she replaced who was doing it before her that might join us later today. So with that, I'm going to turn the time over to Lee and Jake to take us through the slides. And did you get the clicker? Okay.
I did, yeah. So if I can figure this out, I think we're gonna be in good shape. Oh, we're in good. Okay. So our first slide we got is more of the agenda. We're kind of hitting the points that the commission wanted us to discuss in this technical conference. So we kind of got it narrowed down to a few different slides. We're going to discuss smart inverters, the abnormal operations, the recommended settings, and then what the Rocky Mountain Power as far as implementation goes. Then we're going to touch on hosting capacity, kind of our current process and how we determine what would require high penetration circuits, generation capacity, stuff like that. And then there is a request to talk about our virtual power plant, the VPP at
That's the attachment.
a good example is that Soleil Apartments in Harriman. So we can talk about that for a minute, kind of some lessons learned. The benefits.
Yeah, I can go in with you.
The benefits we see from that, and then kind of some issues that kind of have arisen recently. Then interoperability standards, just touch on that, what's kind of called for in the new EEE standard, and then kind of the company's plan for the future and how we're going to drive that connectivity. And then the final topic is going to be on the interconnection agreement. This is where Gillian's going to discuss kind of the process we have for the current level 1, so level 2, level 3 reviews, and maybe some improvements that we can see would be beneficial, kind of some internal ones we've taken to kind of speed up the process. So it's kind of the first slide we got going on for the agenda. So with that, I don't know how this is going to go. Are we going to talk questions, I mean, along the way, or just go through this?
Folks are free to volunteer questions.
Okay, good. We're happy with questions, so.
I just got a chat, sorry to interrupt you, from somebody on the phone saying it's a bit hard to hear, so I guess if we could just kind of speak up.
Talk louder.
Sorry.
Hey, where's the microphone? Is it?
It's in the city, so.
Oh, okay. I'll look up. Okay. So I'll talk louder. So our first slide, let's see, let's go back. Or let's go forward. Is going to be our normal operation. So this is all coming from, I don't know if most people are familiar with the IEEE, the 1547 standard. What's been adopted now is the 2003 version, right? And it's been amended. There's an NA, and then in 12, Brian probably knows better than I do about this, but after, I don't know, what was it, 2003 standard, it was, 25 pages of a reliability standard, or that's the deal. So they amended it, let's see. I'm trying to think of how we want to go, if we want to just go into this or go into the background. What do you think?
I think
Just go straight into this?
so they amended it in 2018, and it went from 25 pages to 140 pages.
About 140, yeah.
So a lot more standards to go through.
Yeah, that's true. So we'll just go through this. So one of the big things, one of the changes that we're seeing from the new updated standard is the normal operation for inverters, right? So we're going from what was originally adopted in all of the existing net metering customers today. We all have them set at the constant power factor mode, right? So everything's at unity. We set the inverters, there's no regulation, there's no active, there's no passive regulation. So now it's defined into two categories. There's category A and there's category B. Again, this is for the normal operation for your voltage and your watt and bar power control. So a little bit into category A, it's mandatory to have the constant power factor mode, and then the volt reactive power mode, which you're going to hear a lot, is volt bar, and then the constant reactive power mode. Now category B includes all of category A, but it also incorporates the ability to do the volt watt mode. So that's you're tracking your voltage, but you're changing the watts. Yeah.
What determines if a category A versus B? I'm assuming there's some definitional difference.
The category, it's just a setting, right? So category A, it makes mandatory the constant power factor mode, the volt var mode, and then the constant reactive power mode. And B, just it widens the capabilities of that inverter for the regulation, right? So B is going to be all of category A, plus it allows for your active power, reactive power mode, as well as your volt active power mode, which is your volt watt. You'll hear that a lot too, volt watt or volt var. Volt var is where a lot of utilities, and it seems like pretty industry-wide, are kind of settling on, is that volt var control. So that's kind of where we're going with category A versus category B.
Can any inverter size, is the A and B changed by size, or is it by?
No, so okay, that's true, that's a good question. So what's happening is with the new IEEE, the 1547 2018 standard, they came out with a 1547.1, which is the kind of the testing standard, right? So then you'll hear people talk about the UL 1741, which is the testing that certifies against the IEEE standard. So there's different versions of the UL standard, right? There's 1741 SA, and that was kind of the one that I believe incorporated like the California and the Hawaii rules. And then now you're going to hear UL 1741 SB, and that's going to be the one that certifies against the new IEEE 1547 standard. So what this is saying is every inverter manufactured that has that UL 1741 SB certification has the capability to do category A or category B. So they have to be able to do one or the other, or they have to do both. We just have to select which one we want. So that's kind of why we're here, right? So you have all these options. We have this wide range of things, and we're saying, okay, you know, do we want to do category A or do we want to select category B? And we'll go into that in a little bit. Is there any questions on the normal operations of that? It's
Older inverters have all these same capabilities.
the older inverters do not. No. So the older inverters, which are, I don't know, they're not smart inverters. They don't have the capability for voltage regulation, right? So we don't have the ability to kind of fluctuate the bars to match, like if we have high voltage to reduce the voltage, and if it's low voltage and we can raise the voltage, because it's set at unity power factor, right? So unity power factor, there's no bar support. It's just constant. So if you need to push power back, you got to raise the voltage a little bit. So that's why you're seeing a lot of the high voltage issues with high penetration of generation.
So they do have the constant power mode
Yeah.
factor, the very top one. That's the only functionality that those have.
Okay.
So everything below the top line has been added in functionality with the smart inverters.
With what time frame are we talking about?
Yeah, good question. We have a slide on
Yeah.
the time frame, and maybe if we can wait to get to that, we can walk through the standard and what.
Yeah,
what
we
arrived
can
at.
do all that, and with IREX help too, we can go into, you know, the timing of everything like that, because there's definitely some. Our next slide, it's going to go over our abnormal operation. So that's, you know, this is the last slide was inverters under normal operation, right? Your voltage is within the limits and everything. Your abnormal operation is going to be you get voltage, really high voltage, really low voltage. You're going to get your frequency kind of out of your bandwidth. And so these new inverters, what they do is they have these categories for abnormal voltage. So you get category 1, 2, and 3. And again, it's something that needs to be selected, right? So they come pre-programmed. Every inverter that meets that new certification will have the capability to do category 1, 2, and 3. So we just need to select which one we want to incorporate into our settings. And again, you know, category 1, we can go through this if you want. It's essential bulk power system stability reliability needs and reasonably attainable by all DER technologies that are in common usage today. So I think what that's saying is basically category 1 is what the inverters today do. It's just the standard. Have you got any more text? Can you hear me okay?
Oh yeah, she's fine.
Okay, all right. And then category 2 is kind of where it's the update, right? So it's kind of meets right in the middle of where the needs are. So it covers all BPS stability, reliability needs, and it's coordinated with existing reliability standards to avoid tripping for a wider range of disturbances. So that just kind of broadens the range, right, of disturbances, the high voltage and all that. In category 3, that's the land where we want to play, is based on both the BPS stability, reliability, and the distribution system reliability, power quality needs. And it's coordinated for interconnection requirements with very high DER penetration, right? So that's where we're seeing a lot of generation compared to the load on the circuit. So you're going to hear a lot of minimum daytime loading, DER penetration, high penetration, hosting capacity. So that's where this category theory comes in, and it allows for the ranges to accommodate examples of high penetration areas. It's where the generation is creeping up to meeting the load, so we don't have excess and reverse flow at the circuit breaker. So that's what that's all.
I know this is a separate topic, but is there a difference in these when it comes to their ability to ultimately, be sort of part of a grid forming inverter system? Do you have to be in category 3 or?
As far as to be a grid forming, no, all three categories would allow for a grid forming.
Okay.
Yeah, it's just the range that you want to do as far as they have normal operations. So
Okay.
all three would qualify for grid forming. Yeah.
Trying to kind of think through how this fits. Does the Soleil lofts fit into one of the three categories? Is that?
No. So,
Okay.
so basically, yeah, so what Soleil lofts is, and we're kind of incorporating it, now, but when we first interconnected them, they were just incorporated as just standalone inverters with no voltage regulation. They were all set to unity power factor, and the same read-through requirements that don't exist when they happen. So if there are any disturbances on the system, of when they first interconnected, they would all trip offline.
I see. So what you're saying is the inverters that they have are actually a tier below where we're moving to now. These smart inverters.
The inverters they have the capabilities to be programmed with these settings, but they aren't 1741 SB certified.
Okay.
I think they're SA certified.
So if ever you were to program the capabilities, does that mean what you just said? Does that mean that the current inverters that they have wouldn't be able to be qualified for this, or the current ones that they currently have, would they need to be swapped out, or?
Yeah. So if we were to adopt the rules that say starting on this date we need every inverter to meet this new certification, then any inverter installed prior to that date is fine. But if Soleil lofts came in a day after with the applications, with those inverters, they wouldn't meet that standard.
I understand, but they're fine for now. Okay.
They're good enough.
Gotcha.
Yeah. In fact, we worked with them a few weeks ago with their inverter manufacturer and worked with the settings to get some active voltage regulation. There's a slide on here that goes over that. We did have some voltage issues out there.
Well, thanks for helping me fill in the color on that. Thanks.
Yeah.
Yeah, maybe some context for this as well. What abnormal operations means is inverters now, if there's a system disturbance, so if we have a fault on our system, like lightning strikes it or a bird runs into our line, that can just momentarily dip the voltage. And right now, if the voltage happens to dip below 0.9, 90% of normal, the inverters will trip offline. And so if there's a system-wide issue or disturbance, transient voltage, then a lot of inverters could trip offline, which then consequently can cause system variability issues with stability. We could lose more generation, we could start to lose load. So this new settings suite allows for that type of system issue to be ridden through. So that's what this new functionality in the inverters does, and it gives us just some options in how to set it with these three categories.
Thanks, Jake. Okay, so another topic we wanted to hit up was our sort of recommendations for what the settings we anticipate being set, right, for every inverter going forward. Once we have that implementation date set, then this is kind of how we would like to have our recommended settings. So we're not calling them default settings because we don't feel like every single one is going to be set for this, because we might have pockets in our territory that might have to have a different sort of regulation, or maybe a voltage setting outside of the norm. But as far as a recommended setting, this is kind of what we we're gonna go with, or would propose. So, the first one, you know, we kinda talked about on that first slide was the normal operation, where you either had category A, or category B. And category B basically is a setting that allows for all of the regulation, options, right? So, even though if you go back to category A, that volt bar is category A, but we wanna have the ability to if volt bar isn't enough and we wanna go to volt watt, then volt watt is a category B setting. So we just wanna have that flexibility to do that in the future, or on certain geographical areas, once it gets identified. So that's that first one for normal operation and voltage regulation is category B, we wanna do with the volt bar. And for the abnormal operation, we've decided to go with category 3. We feel like that's kind of, we've looked around and discussed with other utilities, and the way that the parameters are and the ride-throughs and all that, it seems like category 3 is the way to go. So we're wanting to go with category 3 on that one. And to go along with those recommended settings, this has been a topic of discussion in other parts of our company, but we're gonna post these settings, right? So we're gonna come up with these default settings, I call them default, they're recommended settings, and we've already got them. We've got them created, we've got the file, there's databases where you can store them, but we're gonna be transparent and have it available and easy access, posted externally to our website. We put it on our Power Clerk website if we want, or a link to the settings, but we want it to be readily available for any contractor, homeowners doing the stuff, can just pull those settings and know that they're getting what we're wanting to do. So, and that picture, that's not the full settings file, but that just kind of shows you what it looks like, right? So you get your I don't know if you guys like reading relay settings files, but we can go through that if you want. But you have your voltage, your V lows, your V highs, your F's is for frequency, and you can see over on the right column, you've got your parameters, and those are just the default settings from the IEEE that came out of the IEEE standard, that 1547/2018. And you can see the power factor mode's disabled, the QV mode is enabled, so that's where our volt bar is set. So, and then we have our curves down there, the V1s and Q1s and 2s and 3s. So that's kind of what we're proposing to do with that. So when we have these settings, it's not gonna be something to where contractor won't know what settings to use, right? But they're gonna be there, and the way I see it, it's gonna come from the engineering review. So there's gonna be a process where, as we're going through the review, whoever's doing the review is gonna select which settings file that needs to be uploaded to that inverter, which I would imagine the majority of them are gonna be what we call the recommended settings, which is on that slide. So there is a little tweak that we're gonna recommend for the voltage, the volt bar settings, and we'll go over that in the slide next. And then if there are alternative settings, we'll provide those as well. I don't think we have a need to have a whole bunch of files to download on our website, but I think if we have this first one, it's a start, and then if we come across one where we need a special, circumstance, we'll just create them based off of this, and then not personally, but send it over, so make sure they have it. So they don't actually have to do the settings themselves, we'll provide the settings. So I think that's a piece of the puzzle that is solved there, doing that, so we'll provide that.
Could you give an example of a scenario in which alternative settings, like that deviate from the recommended settings, might be necessary?
Yeah, so this is new to us, right? So what we're recommending is that volt bar, right? So it's when you're measuring the voltage, and if it's either gonna consume or produce bars to either raise or lower the voltage to keep it within those limits. If that's inadequate, if we find, if we set it to that and we're still seeing some disturbances or some power quality issues, reliability issues, then there are other options, right? There's the volt watt option. That seems to have a little bit better voltage control. From experience, I don't have any experience with the volt watt control, just from reading some studies and stuff. It seems like that's the next step in the voltage regulation. Problem with that is that limits the output of the inverter, so the homeowner or the customer might not see the full output. Whereas the volt var, when you got normal voltage, the vars will be zero, so you still get the full benefit of the watts, the watt output, the generation.
Thanks, Lee. We do have a specific example in our territory. So I can't remember the year. About five years ago, we commissioned a study with EPRI to look at our settings and how smart inverters might integrate with our system. And most of the circuits that they studied, the default settings did work. However, they found 1 or 2 circuits that it did not work. And the example I can think of is if we have a circuit, and this was in southern Utah, where we had high load and we also had high generation and high voltage. So we had high penetration, high load on the circuit, and that consequently caused high voltage on the circuit. In volt var mode, what it does is it starts to consume vars. And when it starts to consume vars, now the current at our circuit level goes up. And so it starts to overload even more of the circuit. So at that point, that volt var setting actually hurts another part of the circuit. Even though it might lower the voltage, which is what it's supposed to do, it's going to overload the circuit. So in that case, it's not the right setting to use. So in that particular one, we would have to look at another mode that would help the voltage and not overload the circuit.
Okay, that's helpful, thank you.
Yep.
Would you envision applying those settings like on a case-by-case basis only if it's like a detailed study, or maybe on like a circuit, like if they're connecting to a specific circuit, but it's still like a residential system, it might get different settings? Do you have an idea?
That's a good question. I think it's going to be a combination of both. So a particular study might show that that's an issue, and then that would flag us as say this circuit is an issue. So going forward, we wouldn't have to do an individual analysis every time. And then if we do, our distribution engineers also do 5-year studies, and so as we incorporate more generation, this type of analysis will be incorporated into our typical 5-year study planning process, and we'll be able to start seeing some of these issues as earlier, and so it's not just focused on interconnections, but hopefully we get a little jump on it. But I think it's a combination of both, yeah, as we're learning from this.
Could I ask about your reasoning as to like why not to recommend the volt watt as a normally turned on function?
I think it's a need base, right? Because the volt watt function does take away some of the output from the inverter, so they're not going to be able to produce as much. Yeah. So we lean towards the side of not causing the interconnection customer, I don't know if harm is the right word, but not taking away from their generation capability. So we're looking at that first, and so I would see it as secondarily. If that doesn't work, then we would go to that as the next step.
Yeah. Is there a way to measure how much of a detriment that's causing to the exported watts and account for that mathematically?
Yes, yeah, it would be based on what we would come up with for settings. So on the next slide, we'll show you what our volt var settings look like, and that'll kind of give you an idea, because there's a graph. There's a similar graph for the volt watt mode, and so depending on both of those modes work off of measuring voltage and trying to adjust the voltage based on varying the inverter output for either watts or bars. So yeah, we will set it and according to a graph, and then that graph will determine, depending on what the voltage is, how much watts are output. So yeah, you'll be able to see in the setting in the graph what that looks like.
Yeah.
In fact, maybe we can go to the next. Yeah.
We have it.
It's very similar to this. It's behind me. I didn't know.
Yeah, so like Jake was saying, this is, I don't have the graph for volt watt. So this is the volt bar graph. What we did was we kind of laid the two graphs on top of each other. This is the 1547 default settings. That's going to be the red line. And then we overlaid, or not, we didn't overlay, we just put down our recommended settings, what we'd say, you know, where we're adjusting just a little bit of the voltage on the higher end. So if we start from the left, the top left, you know, that's going to be where your V1s and your V2s are set at 92%. This comes from the default settings for IEEE. You're at 92% of your starting one. So at 92%, you're at 44% of VAR, right? So I don't know, it's a technical conference, but we can get into that. So your VARs are going to be what helps regulate the voltage, right? You either when you increase your VARs or decrease your VARs, you're limiting the output of real power, right? So you get your parent power, your real power, everything. So we start there. We're matching the default settings for the IEEE standard on the low voltage, and then on that bottom screen, or on that, it says 117.6. That's where we get into our normal voltage. So our normal voltage starts at 120, right? That's kind of our base. V base is 120 volts. That's your wall outlet. That's why you hear 120 volts all the time. And then as we extend out, we go 123.0 is going to be our first change to the default settings for IEEE. So they go to V3 is 1.02, and we're going to 1.025, and we put a little note in there why we're doing that. 1.025% of 120 volts is 123 volts. And so a lot of times at our substations, the typical substation, we have it set the voltage at the sub at 122.5 to 123 volts. So at the subs, we're already at 123 volts. So we don't want to start regulating that voltage until we kind of get past what we're already at the substation. So we got a little change there. We're still well within the range that's allowed in the IEEE standard. And then we actually, if you follow the blue line down to 126.6, we're gonna get to full support of that voltage regulation a little bit sooner than the IEEE recommended settings, default settings, and that's just to get a quicker response when we're having some over voltage. So we want to get our voltage down a little bit quicker than the default settings, and again, that's still within the settings to do that. So it's pretty similar. We discussed this with other utilities. Idaho Power has something, they go a little bit further out than what we're doing, and I think they were following some New York utilities and their deal. So it's, I don't know, it seems to me like it's a common practice to kind of stay with the default settings on the lower voltage side of the IEEE standard, and then kind of pinpoint or kind of, you know, get into the details on the higher voltage, kind of how you set your voltage settings. So that's what that slide's going over. Is there anything else, Jake, on that you want to discuss?
No.
Are there any questions on that
Did
one?
that kind
Does that help at all?
of answer your question?
I think so. I'll ask some more if I can.
Okay, so we're still sticking with the recommended settings here. This is the ride-through requirements. This is that category 3. Remember how there's that category 1, which is kind of the standard now, and then it kind of widens the ride-through requirements. So we just selected the table. This is from table 16 from the IEEE standard. You know, you got your C standardize of any voltage over 1.2 per unit, 120% of 120 volts, and then you get your other operations between 110 and 120%. You've got a minimum ride-through time of 12 seconds, and it's gotta operate in plain white 3. These are from the standard, these you really can't change. But it shows you the ride-through requirements, and it shows the continuous operation. So if it's within 88% and 110%, that inverter is gonna stay on. It's gonna continue to operate, whereas in the past, it could trip offline for any reason. So now it's got a mandatory operation and a continuous operation. And I believe, and if there's a lot of questions on this, it's gonna take me a minute to explain, but we can hit the good points. This is the graph that is associated with that table we just went. So these are the category 3 ride-through requirements, right? So that line up there in green, you got that dotted line, that's one per unit, right? So that's at 120 volts, 1 per unit is 120 volts. So that's 120 volts. So it goes up to 110% and down to 88.88 per unit. So if it's in that line, that voltage, that inverter's not going to trip offline. It's going to continue. So you're going to get that ride through. Whereas before, if you got some fluctuation, they would trip offline. And we're talking thousands of inverters. So every new inverter going forward is going to become set with these with category 3. So we feel good there. If we're looking below the green and to the left, the mandatory operation capability, you can kind of see it goes down to 50%, and then the axis on the bottom, the x-axis, that's going to be your time. So you can see it's mandatory operation from 50% for 10 seconds, and then momentary cessation to 0 for up to a second. But then the gray, that's where it's gonna trip. No matter what happens, it's gonna trip. And you can see it's all over the place. But once you start looking at this graph for a few months and think about it in the middle of the night, it makes sense to you. So the shall trip, anything longer than 20 seconds, if we're looking at that one dot, 21 seconds at 80%, it's gonna trip. But it won't trip for 20 seconds. So it's gonna wait to see if that disturbance is gonna fix itself, right? If we have a fault, if we have a frequent or a voltage fluctuation to where it's a temporary in nature, right? So we're just giving it time to everything get back into that green range, and then everything's good. So we love this idea. We don't like the existing generators, the inverters just tripping offline. It's not good for the system. It's not good when they come back on. It's not good when they all go off at the same time. So this is a really big improvement in that standard. So we're looking forward to doing that. So that's category 3. Category 2 is a little bit different mandatory operations and cessation capabilities, but it's more or less, we feel like in discussing with other utilities as well, category 3 is kind of where we want to be. I think IRA would support that too. So that kind of goes over, and Jana, you said 30 minutes, but we got a few slides.
I said 30 minutes plus questions and discussion, so I'm still right.
So now we're into our smart inverter implementation, right? So this is kind of what we're kind of going through a brief storyline idea and a timeline of why you see a standard that was published in 2018, now it's 2024, and we're still not having inverters to this, right? So basically what we're saying here is 1547 2003 was the original standard, and then in 2018 the new standard got published, and then after that, then we had to get the testing test procedure standard. That's the 1547.1. That came out in 2020. So now we're 2 years later. So then after that .1 came out, then UL listing had to come up with their certification. So that came out in 2021. And if Brian nods his head, I know I'm right. 2021, 2022?
They had to modify it in September or October of 2021.
Okay. So we're good there. And then, so what we're seeing is originally, you know, when we first started, we have some Oregon things that we were dealing with on the other side. We originally thought, man, we can start implementing these smart inverters in beginning of the year 2022, and then it moved to 2023. The middle of the year 2022, then it was like January 1st, 2023, we're good, we're gonna do it. The inverters didn't have time to meet the new standards, right? So they had to, the manufacturer had to make sure their settings were dealt. They had to go through the testing process, they had to get that stamp of approval, then they had to make them, right? So we finally feel like we're at a point where all these manufacturers have the ability to keep up with the demand and the availability for the consumers to purchase a SB certified inverter. So we feel like we're to a spot now where most inverters, if not all, I'm not seeing a lot these days unless they're old inventory from some contractor that has it in a warehouse that don't meet this standard. So, in that last bullet there on the bottom, our recommended start date is we're recommending June 1st, 2024. So, with it being March, so May, June, so less than 3 months of requiring every inverter that is applied to interconnect to the utility meet that standard, have that certification. So that's IEEE 1547. 2018 and UL 1741 SB. Those are kind of married together, right? So you say one, you kind of mean the other, but it's probably good to say both. So that's not to say that, you know, May 31st you can put in that doesn't have that certification. That's fine. But going forward, June 1st, anything after that goes through in the queue would need to have that certification. And with the settings provided, with that active voltage regulation and everything like that. Is there any question? Yeah.
We're just trying to think about the rulemaking process a little bit here. Mike's smiling at me. How much numbers? Well, from the company's perspective, obviously we may or may not have the same perspective, but from the company's perspective, how much of these need to be in the rule? How much is something that the company thinks they can just do without worrying about a rule? Because we're thinking timelines, this June 1st for rulemaking seems slightly tight.
Right, yeah, so if I'm not mistaken, I think I went through the rules and there's a reference in the rules of the IEEE standard, and if you follow that, it references the most recent version of the IEEE standard. So we feel like even today that if you read the rules, that we should be following the most recent version of the IEEE standard, which is the 2018. But I mean, we just feel like that's a good time, and it's a benefit for the customers and to the utility, the grid.
Thanks.
Mm-hmm. But as far as rulemaking, yeah, June 1st may not be acceptable, but that's just kind of our recommendation.
Is that company-wide, right? That was kind of the
Yeah,
date
so
we picked
that's
for
why
all
we
6
decided.
states.
So yeah, so we chose June 1st. It was gonna be May 1st, but yeah, in Oregon is through their rulemaking process is June 1st. They've landed on. We've met with all our regulatory folks in all the other states to kind of go over it. And so with all 6 states in our service territory, we're shooting for June 1st to require that. So that's Utah and Idaho, Wyoming, Northern California, a little bit of Washington, and Oregon. And also because it makes it easy to do it all at once instead of one state here and a state here and there. But we feel like that would be beneficial.
Can I ask an additional question?
Of course.
Besides, I guess from the Soleil lofts, I was just wondering, besides the smart inverter, additional features that could be, could serve the system better, how is the integration with the software working that you developed through that Soleil, or maybe you moved on to a new software? does the company feel confident that with the smarter inverters, that the tracking of all the DER resources, you know, and managing those within your system, is that going well, or is that problematic? Or besides the smart inverters shutting off, like you've been saying?
Yeah. So as far as here, I'm going to skip a slide and we'll go back to hosting capacity. So we can talk about the Soleil lofts first. So what's going on with Soleil lofts is if everybody's not aware, it's an apartment complex in Harriman, Utah. Of course, we're in Utah. It's 600 and so many odd apartments, 612 or something like that. And each apartment has its standalone net metering project or system, right? So it's got 7 or 8 kW of solar, and inside each apartment unit is a battery. So we got a solar and battery, and all 600, we'll just for easy math, 600. They're all tied to what we're calling the UVGMS, right? So we came up with a distributed battery grid management system, with working in cooperation with Sonnen. So what they did is they created a kind of a dashboard or portal or whatever you want to call it, and so we have access to all 600 batteries, and we actually have more than that, right? So it's not connected to the inverters, but we're connecting to the batteries. So it's two sort of communication connections we're talking about. So interoperability and Soleil lofts kind of are two different things, right? So we're managing the batteries. It's part of the Smart Battery program, which people might have heard of before. So in addition to Soleil lofts, we've got thousands of batteries in the valley in Utah, and even in Idaho now that they're approved to do that. So we have connectivity to the batteries. So we'll just go through the slide, and then I think your question is going to be in the lessons learned deal. Well, I already talked about all those on top. So basically, if you're not familiar with Soleil, we have it set up for frequency response. We can use it for peak load management. We can use it for circuit congestion, and among other things, right? We can use the batteries. We can program them to charge in a certain amount of time. There was an issue last summer where the batteries weren't getting charged enough during the day, so the solar. So we had to extend the charge time. So we went into the management system and programmed the time to, okay, we need these buildings to charge at a better rate, so we extended the time. So we have the connectivity for the batteries, and we feel like it's been a good project from a learning perspective and everything like that. And we've also for Soleil, I used to be a field engineer, and where Soleil was my area of responsibility. So I worked pretty close when they were designing it, and we've done it to where we have circuit loading, right? So circuit just looks like a sine curve, right? And you get peaks during the day and valleys at night when your load's down. We determined and we verified that we can, if we need to reduce, I mean, we've got 5 megawatts of battery reserve just available at any moment in time. So we verified that we could use that for peak management. If we kind of see like the characteristics of the distribution circuit, or even at the substation transformer, if we see a need to say, okay, we're getting pretty close to overloading it, let's just wait for that. Let's go from charging the batteries, and then we'll dispatch the batteries at 7 o'clock at night. We just full dispatch. We got the whole thing. We do see benefit of that, so that one's been good. The main thing that we've used them for this last year is for frequency response. That's where our operations group, if we have any disturbances on the grid, could be in Wyoming, could be wherever. We have a big fluctuation, we got big load drop off, we got generation drop off line, we got a big fault somewhere, and we see this that frequency go out of our stability. Those batteries, we send a signal to them, and within really a handful of seconds, 5 to 7 seconds, we have all 600 batteries injecting that power to help stabilize the system. In addition to everything else we have, but there is some benefit to that.
Can I ask a question about the, do you manage the WattSmart batteries the same, and the Soleil batteries the same way? Are there meaningful differences in terms of how you manage or dispatch those batteries?
They are, I want to say that they are all set up for a frequency response. So I think they're all tied to the WattSmart program now. It didn't used to be that way. So we have an individual that kind of manages that group, but I work pretty close with it, so I know enough to get close. So the batteries at Soleil, they're kind of tied to their own cluster. We just call them clusters. So we have the Soleil cluster, and then we have all the others in the valley. So but they're all tied to the frequency response and everything. But if we want to do like a peak shaving on that bang intercircuit, it's a bang intercircuit distribution circuit, then we pick the Soleil cluster to do that, and we wouldn't do that for the other cluster. But they are tied together. They're tied together, but they're grouped separately.
So you could dispatch them differently?
Yeah, we could. Yeah, we could do Soleil separately. Now we can, because we work with Sonnen pretty close, right? So if we need to come up with another geographical area, because right now it's all or nothing for the rest of the batteries to dispatch. But if we need to use like a specialized area for peak shaving or for whatever it could be, then we can probably work with Sonnen to kind of configure that, a new cluster. So to answer your question, we do have connectivity, but we don't have full, configuration capabilities, right? We still have to go through Sony. We got to get with their engineers, and they're in Germany, so we have to have early calls with them because it's late for them. But we do. We can get those changes done, but it's been good. But that's not the same as the interoperability because we're not connected to inverters. We can't make any inverter change, any settings changes or anything like that.
Gotcha.
But we have worked with Soleil had SMA, Sunny Boy inverters. We were on a call with them going through the lessons learned. So we have used it for frequency response. There was an outage last year on that circuit where we have verified that there was an outage. If it weren't for that batteries and their grid, microgrid, then they would have been out of service. But they did have that ride through, and they did verify that they made it. they remained in power. So that was a good case there. It's been dependable. I wouldn't say 100%. I wouldn't say 95%. There's 600 units. There's always something wrong with one of the units. They're all Wi-Fi connected. There's a lot of Wi-Fi connections. Customers unplug things all the time. But that's what we're finding, right? So we're dealing with that. A lot of connectivity deals. But one of the big things that we've seen and we kind of saw. You had a question?
Well, finish your sentence.
Oh well, I can stop talking. I've been going for a while. You want me to keep going, or you want to go?
You go ahead.
Okay.
I just have a general.
So this last summer, Soleil contacted us and said, "Hey, we're getting some high voltage," and we said, "Well, yeah, we have 600 batteries, and things connected right there. You're gonna have high voltage." And so we did some testing, we did some measurements. We found some three-phase transformers around. We had recorders set at their transformers serving the apartment complex, and they had high voltage, but not outside their complex. So we had it narrowed down to the reason there. We lowered the voltage at the substation, lowered the voltage at the homes a little bit, but they're still getting high voltage. So we came up with an idea, not the idea, but we came up with a solution. We met with the SMA, talked to them, said, okay, what can your inverters do that they're not obviously doing now? Because right now we found out that they were set to unity power factor. We're like, well, okay, that's step one. Let's change that. So they did. So even though I said earlier they wouldn't be stamped for that SB certification for that UL, they do have the capability to go in there and basically do their own settings to do that. so they were able to incorporate that voltage curve that we showed you, and along with those recommended settings. So that's kind of our first example of, okay, this is going to be our volt bar control with that voltage profile out there. I don't have any news for you yet because right now they're programming it. So we can come back and give you an update once we know if it fixes it or not. But all signs are showing to it going well. And then that last bullet, as far as lessons learned, and this is just me dealing with the owners there, the managers out there, is we see a lot of outages on certain buildings at a time. And we're like, what is going on with these outages? We're like, you're missing 100 batteries are offline. We're like, oh yeah, well, we took those out because we had to change all the AC disconnects because there was a defect in one, and they were getting water behind it, and they were tripping everything offline. So one kind of lessons learned is, you have one thing, one unit at 600 times, and it's a bad unit. You have potential issues for a lot more problems. So that's just kind of a lessons learned we saw out there. Okay, I'm done. You can.
So, just a question about how you actually interact with these batteries. I can see that from the customer perspective, they would want the energy that's being produced in one of the battery, and then they would want to use it. And if they export it, they get a lower rate. So when you talk about using the batteries, are you using the power they've generated, or are you charging the batteries from the grid and then pulling that back? Or how do you do the accounting of the power you use versus the power they've generated?
Yeah, I think I can explain it. So what happens is there's a cycle, right, that these batteries go through every day. So if we start in the morning, we're going to say that the batteries, is low, right? So then the sun comes up. So then the solar panels start generating. So the first thing that those solar panels do is charge the battery. So it charges the battery up to 100%. And once that battery's fully charged, then any excess solar goes to support the load in the apartment, right? And then if there's any excess load after it supports the load in the apartment, then that goes through that bidirectional meter, your net meter. And that's where you kind of capture the credits there, or the kilowatt hours of generation. And then as the battery's charged, and then the solar, if there's excess solar, the battery's just sitting there in standby mode because the solar's supporting the load of the house, and then it's exporting. And then let's say solar output decreases, load in the house increases, well then that battery's going to support that difference, right? And then the solar goes away, and then the house still needs load. The battery's gonna be utilized to support that load until it gets to a certain percentage. And when we use those batteries, we're only using them for 5 minutes at a time for that frequency response. So it's very minimal. You don't even really notice it. So if I'm saying it right, and I think Soleil's set up like this, we just require a state of charge of 20%, at least 20%, to be able to use. So, the homeowner has full availability to use that battery as they want. We just need to have that 20% reserve just in that instance.
And we do offer an incentive in the WattSmart battery program. There's an incentive that we provide to offset the cost of the battery, and I think that's the deal. Is we get to use it for frequency response, and we'll be $1,000 or whatever it is to install the battery.
Yeah.
But you don't actually keep track of how much you're using in terms of recharging it or reimbursing them. It's just
not that I'm
No,
aware of.
in fact, when the battery's discharged, if it's more than their load, and it goes through that meter, then they'll get that kilowatt credits for that discharge, and then it'll be. So there are times where the batteries do.
Oh, so when you use the battery, it goes through their meter to get to what you're using?
If the available capacity of that battery is greater than the load at the house. Yeah, so
I'm saying if you
yeah.
trigger your event where you want to withdraw
Yeah.
energy. It goes through their meter to get to your event.
Yeah.
Okay, all right, thanks.
Yeah.
I have a question.
Yes.
So on June 1st, 2024, will Rocky Mountain Power have more capability in terms of using the Soleil apartments for, you know, more than just frequency response, or, you know, will there be any benefit from,
Well,
is that clear?
I think so. Were you gonna say something, Drake?
No, I don't think that we're gonna have any, the contract is what it is. The only thing we're changing on June 1st is the implementation of smart inverters in other locations for new installations. So we're not gonna go back to any other installations that have been installed. So they're pretty much grandfathered into what we have now.
Is that limited by the contract? I mean, if you didn't have sort of a contract set in, you know, with the terms and conditions of how you're gonna use this, could Rocky Mountain Power use Soleil for, you know,
For peak shaving.
additional, yeah.
For peak shaving perhaps.
for
So
everything.
I believe it is in the contract that we can use it for, I don't know the particulars of what we put in place for that, but my understanding is we've been able to do testing with it, and so if we actually needed to utilize it, then we can. And that's now, that's not a June 1st thing. That's a good question. I'm not exactly sure what the particulars of the contract and what we are, I'm not sure if there's a limit to what we can do, is that
Right,
the
I think
question?
that's,
Okay. All right. So we'll go back a slide. This is our slide on hosting capacity. We'll just kind of go through our process that we currently have to determine that. Thank you. These slides are tricky for me. Fine. So each bullet kind of represents a process step and how we do a review. So each application in that metering, it's assigned a queue number, right? So everything, if you put in today, you're gonna be ahead of in line if someone put it in tomorrow. So you don't have to worry about what happens behind you, it's just the queue order. So we do everything based on its order in the queue. And then one of the first steps is we identify what distribution circuit that particular interconnection wants to connect to. And in doing so, we're gonna determine if it's deemed a high penetration circuit, right? So that's when our generation is creeping up to, at, or exceeding our minimum load. We just don't want any reverse flow at our circuit breakers or line reclosers, for that matter. So we'll use some modeling software to determine the existing generation that's installed in that circuit. And then the big thing is coming up with a loading amount, a minimum daytime load. So we take the hours, 8 and 9 a.m. to 6 p.m. To determine what we see as the minimum load. And most of these circuits that we have here in Utah, there's some few rural ones, but we have SCADA, right? So SCADA is our real-time data, so we know that what we see is an actual number, right? So at 11 a.m. on a Tuesday, we see the lowest time. We know at that time and place, if we see it as, let's just call it a megawatt, we'll know that there was a megawatt of load with all the active generation generated. So that's an actual minimum load. And so we'll use that value and then look at the proposed project and say, okay, if you're 2 megawatts and we're showing a megawatt of load, well, that's going to be an issue. And you would exceed the generation capacity on that circuit. Yeah.
So it sounds like it's net minimum daily load for the circuit, because the generation that's already there is offsetting the load, so there wouldn't be an import or anything coming down the circuit,
Right.
right?
Yeah. Yeah, so there's two ways to look at it, right? So we can either use that actual minimum load, or we can use that load and add in a percentage of the existing generation, because we know not all the generation is at 100% when it's at that load. And there's some websites out there where you can go in and say, okay, on this day and time in this region, the solar output was at 72%. So if you really want to get into the details, you take 72% of that active generation on that circuit, and then add that to what we actually saw and say, okay, there's our minimum load if we take that generation off. Or we'll just say the net, if we have SCADA. Now, if we, sorry, Jake.
I was just saying, we have about 65% of our circuits, we have SCADA, so we measure exactly what the load profile is on that circuit, so we know what the date, we just look at a point and we know what it is. But for the other 35%, we have to make some assumptions and net it out to figure out what it is.
Oh, well, what I meant was like, so I have PV panels on my house. I may be running my air conditioner when you're looking for that number, but if my panels are producing as much as my air conditioner, you'll see zero from my house.
Right.
You don't see the thousands of watts.
Yeah, exactly, so we will,
That's all I was.
yeah, so at the circuit level where we're measuring, every minute we're measuring what the load is on that circuit, it will see, at your house, it sees zero.
Right.
Exactly.
Okay.
Yeah, and like Jake's saying, if we don't have SCADA, we call them hand reads, manual reads, so we'll send somebody out to check the loading or the relay or whatever it is that they're doing. And then we make a calculation based on that, and then add in the generation to get the net.
Are you planning to roll that out further? Is the plan to eventually get all of the circuits measured, or is it?
Oh, I'd love to get them all measured, yeah, but.
Is it just, or is it like an ongoing process, or is it static, like 65, 35, that's it? Not
It's
changing?
an ongoing process.
Ongoing process,
So
right.
communications is the issue. A lot of our rural circuits, it's difficult to communicate. We don't have fiber to a lot of them. So then we weigh, do we have a cell pack out there? Do we have cell service or radio? So, yeah. The idea, we would love to have it. As engineers, we'd like to know.
But over time,
Yes.
presumably there will be
Yes.
a little bit more and more and more.
Yeah.
And how often do you have to do it for a given circuit? So if a customer comes in and says, I'm gonna put an 8 kilowatt system in, you run the study, you say, yeah, you got oodles of room, or whatever, it's approved. If someone on that same circuit comes in 2 months later, is it a matter of saying, oh, we had X hundreds before, adding another 7 isn't a problem, or do you have to actually go back and redo it, or what do you do?
We redo it, so we look at the loading plus whatever's been approved prior to that second application, and we add in all that to the load, just to kind of, because it's all on queue, right? So we update the values for every application.
But does it have to get remeasured for every application, or?
Now, if it has SCADA, we would take the 12 months of history, and then we'll know what was connected to that 12 months, and then we can find out what's been approved since that minimum was taken, and kind of have that capacity of generation on top of the new one to kind of get calculated.
So it's a rolling 12 months?
Yes.
And where is this happening in the process? So you've got like a 15% max load screen, right? That would do something similar.
Yeah.
But is this being applied on top of that for small systems, level 1, level 2, or are we talking about level 3?
So this happens, in Utah, if it's under 10 kilowatts and it doesn't need an AC disconnect, that's the limit, right? That's the threshold. Under 10, you don't need a disconnect. And it's not been identified as a high penetration circuit from historical analysis, then they just get approved. Until we see, okay, we're getting close to that, so then there needs to be more engineering review done on that, right? So now, when we're doing a level 2, before it gets to a level 3, Well, it's just part of that 15% screen, right? So instead of that 15% screen, we're kind of doing the 90%. Because they all fell in at the 15% screen at this point. So it's during that process.
Okay, so you're not saying you would apply this to a level 3, because for a level 3 you can determine what its effects are if it does backfeed, right? And
Right. Well, level 3 would have failed that screen.
or it's too big, right?
Yeah, or it's too big. Yeah. I think I answered that right.
That makes sense. So it's more of a replacement for those high penetration circuits for the regular penetration
Yeah.
circuit.
Yeah, so that's kind of that last bullet point, right? So we're just checking if there's for any anti-islanding protection. So that's where those level 3 impact studies come in. Is when we identified that reverse flow. Same thing as what we went through in Oregon.
So is that the same threshold that you're talking about for anti-islanding?
It is.
Can you explain anti-islanding? Does that mean like you can't?
Yeah, so anti-islanding is and Jake might be able to better explain it than me, but basically when the generation to load is at 0 or the generation exceeds the load at the breaker and we're getting reverse flow and we have a fault or something happens, there's maintenance at that or something where that causes that circuit breaker to open, we use high speed reclosing. So when you see the inverters, they're required to stop being energized within 2 seconds. But when we're closing in 10 cycles or 30 cycles, 0.3, 0.2 seconds, that's too soon for them to come offline. But if we see that there's more load than generation, when that circuit breaker opens, those generators aren't going to be able to support that load, and they go offline immediately. So our protection and control group has explained that to me numerous times, and so it's just a protection scheme. You know, we do deadline checking. You'll hear that a lot. Deadline checking, hotline blocking, same thing. Basically, it's just some sensors on the 3 lines coming out of the substation, and we're sensing the voltage to where it's going to prevent that circuit breaker from closing back in until all 3 lines are de-energized, which means all the generation is turned off. So we just don't want to close it on energized generators that haven't turned off yet. And then our next step is direct transfer trip. So that's where we send a signal once that circuit breaker opens to trip a generator, usually the larger 3-phase ones that exceed the load. So that's where costs come into play a lot, and it gets complicated, and that's where we get into system impact studies, feasibility studies. But that's where those come.
Now, maybe from a higher level too, anti-islanding is just once you get enough generation on a circuit, there's a potential that the generation on the circuit could support it if we disconnect. And we don't want that. We don't want a bunch of aggregated generators controlling voltage, controlling how the grid is operating without us being connected to it, because then we lose control. So when we talk about it, we don't want that to happen. That's anti-islanding. What's the protection to ensure that does not happen?
Okay.
All right,
So
are you
real quick, going back, I think you started explaining a scenario in which minimum load is at like 1 megawatt on a circuit or 1 kilowatt, I don't know what you said,
Yeah.
and someone wants to interconnect some generation larger than that. I apologize if I didn't follow the whole thing through, but were you saying that they would be denied, or they would be able to interconnect certain generation up to the minimum load, or it would trigger a further engineering study in which maybe they would be allowed to interconnect higher if there are certain protections in place?
Right. So we'll never deny any generation, right? So there's always options to allow it. They might be very costly options, but there's always some sort of protection or upgrades or transmission. I mean, we've dealt with some transmission stuff in the past, and it's So if you do exceed it, we won't say you can't connect. We'll say, you're at a megawatt. If you wanna reduce it down to this much, you can get it approved as is, but if you wanna stay at a megawatt or anything above this threshold, it's gonna require further study. So that's where that level 3 study comes in, and it's typically what we're seeing is the deadline checking if the circuit breaker doesn't already have it, or that direct transfer trip. And that's where it gets pretty expensive for the customer. It's either over fiber, if it's flat, there's no trees. It's easy in Wyoming, Utah, the hills and trees, you know. But we do use radios and communication towers and stuff like that.
Okay, thank you.
So that's all identified in the study process. We have our protection control, our communications, our SCADA engineers get involved and kind of scope all that out.
So for the hotline reclose blocking,